Hi there and welcome to this example video. I'm looking at examples of Ohm's law in electricity. So let's get right to it. This is a slightly more complex example or problem than what we've been looking at, and it involves this circuit here. And let's follow the current as it flows from positive to negative in this circuit. Now notice my coulombs are going to pass out here, my charges. All of my charges is going to flow through resistor 1. That means resistor 1 is in series. Okay, then we get to this point and some of the charges are going down and some of the charges are going forward. So not all of the charges is going through R2, but all of the charges that go into R2 will flow through R2, and all of those charges will again flow through R3. So R2 and 3 are also in series with each other. That's important to note. So that if I were to look at this branch will have a total resistance itself. I shouldn't do it like that, but I can rather imagine these two to be a single resistor. So I'll talk about the resistance in this branch rather than the resistor R2 and resistor R3. I'll consider them as one thing because all of the resistors, all of the current passes through R2. Not the total current, but the current that comes into this branch goes through R2 and through R3. Okay. In the other branch, we only have one resistor, and so all of the current that went this way goes through R4 and nothing else. Okay. Then at this point, the two currents come back together. And so the total current once again passes through R5, which means in the system, R1 and R5 are in series with each other. Okay, and then they give us the values. They say R1 is 5 ohms, R2 is 8 ohms, R3 is 6 ohms, R4 is 11 ohms, and R5 is 12 ohms. And the first question asks us to calculate the equivalent resistance of the circuit. Excellent. They didn't give me anything else so far. So usually if they give me something like current through one of the things, I would also work out the potential difference over that one. But for now, they've only given me the resistance and they asked me to calculate the equivalent resistance. Now, what is equivalent resistance? Equivalent resistance is the total resistance. It is as if I were to make a simple diagram like this. So imagine this was my diagram, and this resistor represented all of the resistors in here combined. What would that resistor value be? And it's simply just adding the resistance, but the point here is that it's not as simple as just adding the resistance, because we can add all of the things that's in series. I can add this one and I can add these two together, but then these split up, and once we have parallel branching, we have to use a method for finding the equivalent resistance of the parallel branch. Okay, so this is how it works. These two are just going to be added together, but for these I need to make use of that effort. So I'm going to say now 1 over the resistors in parallel is equal to 1 over the resistors in branch 1 plus 1 over the resistors in branch 2. Now you might ask me, why didn't you say 1 over R2 plus 1 over R3 plus 1 over R4? Okay, those are all in parallel. They're not all in parallel. There's only 2 branches, so we should only have 2 fractions, and that is why I said we'll consider these two as a single resistor, because they're in series. Okay, and so I'll take 1 over the resistance in branch 1 plus 1 over the resistance in branch 2, which gives me the following. So in branch 1, I have 6 and 8, I get 12. So I've got 1 over 12 plus in branch 2, we have a resistance of 11. 1 over 11. Okay, so my total equivalent resistance would be 11 plus 12 over 121, which gives me 23 over, sorry, 23 over 121, and that is for 1 over the resistors in parallel. So I can flip it around. So resistance in parallel is 121 over 23, which, if I use my calculator, 121 over 23 gives me 5.26. 5.26 ohm. This is for the resistors in this whole resistance. So in the end, if I talk about equivalent resistance, it is literally following my main current and adding up all of the resistance the main current will encounter. The main current encounters 5. So the total resistance, and let's change color a bit. Why won't we? Okay. The main current encounters 5 ohm. Then he comes to this point, and he doesn't encounter the main current doesn't encounter this one and that one and that one. No, but he does encounter the whole thing, the equivalent resistance of this parallel branching, and that we calculated to 5.26, was it? Yes, 5.26. And then even though they split, the current comes back together at this point. So we've got our total current united at this point, and then we see our total current also encounters the 12 ohm at resistor 5 plus 12. So my total equivalent resistance is 1022.26 ohm. Excellent, not very difficult. If the EMF of the battery is 19 volt, okay, what does that mean? That means that I am measuring the voltage over the battery, and I get 19 volts. What does 19 volts means? It means that every coulomb that leaves this battery, remember a coulomb is a collective noun for a group of charges, okay, and every coulomb has 19 joules of energy. So we have 19 joules of energy. Now that's when he leaves here. When they come back, they have no joules. They've got no energy left, okay, and therefore it has spent all of its energy proportionately to the resistance. So he would come here and he would spend some energy. We would spend some energy here. So when I measure voltage, I'm measuring the difference between the energy it has here and the energy it has here. Since here he has nothing and there he has 19, the difference is 19. Here we measure how much energy does it have here. Well, it's got 19 joules per coulomb. Then it spends some, and I don't know how much it spends at R1, okay, but after it's spent energy, it's got some left. Let's say it spent 2 joules, just as an example. It spent 2 joules here. Then at this point it would have 17 joules per coulomb. Then they come here. Now at this point it splits up into 2 groups, okay. Some of the coulombs go in that direction, some go in this direction, but the point being that at this point each coulomb still has 17 joules per coulomb. At that point, before it gets into R2, it still has 17 joules of coulomb. Now the important thing about a parallel branching is when they come here, no matter how much they spent, each coulomb must still have the same amount of energy when it comes here. I don't mean the same amount that it started with. I mean this branch, the whole branch will spend the same amount of energy than this branch, so that when they come together, all of them are have the same amount still. So let's, just an example, let's say they spent yes, let's go for 10. Let's say they spent 10 joules in each branch, so that here they come again and they've got 17 joules. Then they've got 7 left because they had 17. So at this point they have to have 7 joules, and at this point they have to have 7 joules per coulomb, so that when the coulombs come here again, each coulomb has 7 joules. And then he would spend all of the 7 joules, and again I'm just using made up values to explain. Okay, so and then all of the 7 joules will be spent here, and so that there's nothing left at this point. Okay, so the reading here would be 7 joules per coulomb. The reading over both of these will be 10 joules per coulomb. The reading over this one, since there's just one, would be 10 joules per coulomb. And then eventually, if I just wanted to know how much energy was spent on R2, it would be less than the 10 joules, because let's say on R2 we spent 6 joules, and on R3 we spent 4 joules. Is it? Yeah, because total it must be 10. Okay, so 6 was spent here, and another 4 was spent here, and so all of it was spent by the end. Okay, point being is that when we add up all of the voltage meter readings over the total, so currents, so total current, this voltage there, and this voltage there, all of them must add up to the total voltage. Now let's see if I can clean this picture so that we can actually do the correct calculation. Okay, that might be helpful. Okay, so our next question is, if the EMF of the battery is 19 volts, we have that. What is the current that passes through R4? Okay, the current passing through R4. Now, let's just start with that and say, well, if I wanted the current in R4, I would take the current in R4, not R4. If I want the current in R4, I would take the voltage over R4 divided by the resistance. Now I have the resistance, but I don't have the voltage. I don't know I know the voltage there, but I don't know the voltage here. Okay, so to get the voltage over at this point, okay, this is what I'll have to do. I know that the voltage is the difference in energy between this point and that point. Okay, now if I take these points back, it's telling me how many joules do I have over between here and between, or the difference in joules each coulomb has between here and here. Now that's what I tried to explain just now. The difference between the potential difference between these 2 points and the potential difference between these 2 points are exactly the same. Okay, so if I can get what is the potential difference at this point and the potential difference at that point, I can have the voltage over these 2 points. But now to know how much energy or how much the potential difference is over these 2 points, so I'm now literally trying to get the voltage meter reading, of the whole parallel group. Now how can I do that? Well, the voltage meter reading over the parallel group is equal to the current that goes into the parallel group times the resistance of the parallel group. Okay, it's simple Ohm's law. And so I have the resistance, I've calculated that already here. There's the resistance of the parallel group, but do I have the current that goes into the parallel group? And I notice here, well, yes, the current that goes into the parallel group is the total current. So the current comes here, all of the current passes through R1. All of the current goes into the parallel group. Yes, it splits up into two branches, but if I'm talking about the parallel group itself, all of the current goes in there and all of the current goes out. So can I get the total current that goes in there? Well, since the current that goes into the parallel group is the total current, I can get the total current. Let's see. So can I get the total current? IP is equal to IT. Can I get the total current? The total current is given by total voltage, which is just the EMF of the battery. It's the total amount of energy that is being spent by each coulomb divided by the total resistance. Now, I just calculated total resistance in the previous question. So there's total resistance. I've got total voltage. So yes, I can get this. Total voltage is 19 given to me. And then total resistance, we had to calculate the previous question, 22.26. 22.26. And that is going to be helpful. Okay, 19 divided by 22.26 gives me an answer of 0.8535. I'm going to try round off as little as possible. 8535. As a matter of fact, I'm actually going to do this. I'm going to say memory store. Just store that value in there. Okay. I've already rounded off, but that was so that I can answer the previous question. So now I've got the total current, and I know the total current goes into the parallel branching. So the total current is equal to the current in the branch. So I've got that value. So I've got the 0.8535, and now I just times this by the resistance of the parallel group. That was 5.26 was the equivalent resistance of the group, the parallel grouping. So I'm going to take this and I'm going to multiply it with, and let's actually multiply with this original value, just to avoid making errors in rounding. Okay, there we go. 4.4904. I'm still not at my final answer, so I'm going to 4.4904. I'm not at my final value, so I don't want to round yet. Okay, so now I've got the voltage reading. In other words, where whatever amount of energy I have at this point, when I take the energy at this point, the difference between the energy per coulomb is 4.49, almost 4.5. That means that in this whole thing, we spend 4.5 energy in each branch. Each coulomb comes in here, this guy comes in with how much he has, and he leaves this branch having spent 4.5 joules of energy. Same thing, whoever comes in here, he spends a little bit of energy here, he spends a little bit of energy here, but in the end, he spent 4.49, so that when they come here, both of them have spent 4.49. So I have the voltage. The difference in potential energy over R4 is 4.49. Okay, so that now I can substitute that. 4.4904 divided by the resistance of 4 is 11 ohm, and that gives me, okay, that value divided by 11 gives me 0.40, and since this is my final answer, I can round to 2 decimal places if that's what the question requires. Although when it's such small values, in other words, when there are no values before the decimal place, I like to do at least 2 significant figures. So 2 significant figures just mean there's 2 values that don't include a 0. So it's 0.4082. so it won't round off. So I'm going to keep it 3 decimal places, and this is going to be in amperes. Well, I know this was a long video. It was quite a complex question, but it's very instructive. I hope you saw that. Thank you very much for watching. I'll see you in another instructive complex question.